Biased competition and normalization. If the last section seemed a bit hard to follow, no worries, it's nitty-gritty stuff. You may want to watch it again and slowly digest it. Maybe you need to pause to read the figures carefully. But once you get it, you may wonder, how does it work exactly? How come the receptive field shrinks in this particular way? The biased competition model was proposed to account for this. The model can be formulated precisely with mathematical equations, but here we are going to try to get to the gist of it conceptually. The following is not exactly going to be precise, but it will help us get started, which is important. There are several key ingredients of the model. The first is something we already discussed. That is, that neurons from higher cortical regions have larger receptive fields. For example, in V4, neurons generally have larger receptive fields than those in V2. In the last class, we already gave an intuitive idea. Why? A V4 neuron may receive input from multiple V2 neurons. In a sense, it cares about the total sum of the regions that each relevant V2 neuron cares about. So let's think about this hierarchical structure, where you have a later stage V4 neuron taking inputs from two V2 neurons. Let's say we put a graded bar inside the receptive field of a V2 neuron on the left, and a dark bar inside the receptive field of the V2 neuron on the right. Because V4 takes input from both of these two neurons effectively, we're putting both stimuli inside the receptive field of this V4 neuron. Now let's say this V4 neuron likes graded bars and dislikes fully dark bars. That is, it is tuned to color or luminance, such that graded bars are preferred, and fully dark black bars themselves are non-preferred, meaning they don't generate a lot of firing. And here's the second important ingredient of the model, which is based on what we observed in the last section. When you put a preferred stimulus and non-preferred stimulus inside the receptive field of a neuron, it would fire at an intermediate level as if it is taking an average, which is to say the two stimuli compete with each other. Say the dark bar generates 20 Hz firing, and the graded bar generates 100 Hz firing. When both are presented, the neuron doesn't fire at 120 Hz. It doesn't add up. Instead, it may fire at 60 Hz, as if the dark bar contributed to dragging things down a bit. Mathematically, you can think of this as giving weights to the inputs. Now, both V2 neurons contribute 50%, so the firing rate may be 50% times 20 Hz plus 50% times 100 Hz equals 60 Hz. So far, so good. This is all before attention comes into play. What does attention do? The idea is that attention may boost the activity of the relevant input neuron a bit, which is known to be true based on many other studies. In this case, for the subject attending to the darker part, the relevant V2 neuron may show higher firing, so the impact to the downstream V4 neuron may also be higher. But this is the most important ingredient of the model. For a V4 neuron receiving multiple inputs, when you boost one of the inputs, something has to give. When we boost the activity of the V2 neuron coding for the darker bar, and hence its downstream input on the V4 neuron, we will also somehow dampen the influence of the other V2 neuron has. This is at the core of the idea of biased competition. If we see the two V2 inputs as competing for influence on V4, when one gets stronger because of an intentional boost, it may quench the impact of the other, in a fashion sometimes called winner takes all. Or think about the equation again. When we say each of the two input neurons has 50% contribution to the downstream V4 neuron, we mean to say their total impact to add up to a 100%. You can't boost the impact of one neuron to 100% and keep the other at 50%. That would be adding. Instead, what we want is weighted averaging. 50% times 20 Hz plus 50% times 100 Hz equals 60 Hz. So this is essentially the biased competition model. When you boost the impact of the relevant input neurons to a downstream area, you dampen the impact of the other unattended neurons because they compete for impact. This leads to effective shrinkage of a receptive field, as if the downstream neurons now only listen to the attended, ignoring the unattended. The process of how the downstream impact of a group of neurons remains more or less a constant is also described by a very well-known framework called normalization, or divisive normalization. Normalization can be expressed in precise mathematical equations, though once again, we're not getting into such details here. The basic gist is that within a cortical region or subregion, the total amount of downstream impact cannot go up infinitely. When one group of neurons is boosted, the total firing of all neurons concerned needed to be divided up again, so those who aren't boosted are effectively dampened. So this is a lot like what was described in the bias competition model. The normalization model is not just applicable in the context of attention. It looks like how cortical neurons behave in general.